Welcome back from coffee, everyone, and from a very entertaining photography session. What an excellent sense of humor she had. Matthias was clapping his hands in anticipation of this lecture, I think. No, I think that was the signal. Okay, so today what I'm going to do is derive for you the Hellings and Downs curve. And I heard that Bruce already did this for you in one way. I'm going to do it in a slightly different way, which is my own way. Hopefully one of those ways resonates with you and you like it. I've also tried to answer some of the technical questions that I got during my previous talk in this talk, so I can show you all the technical details, including the pulsar terms, which is one of my favorite things. So I'm so happy I get to do a deep dive on pulsar terms in the stochastic background. And before we get started with the actual derivation of the overlap reduction function or the Hellings and Downs curve, I just wanted to do an order of magnitude estimate with you guys because it's fun, but it also helps you understand why we ever thought that there could be a stochastic gravitational wave background, right? Has anyone just stopped to be like, why do we expect this to be true? Like, how do you show that there's a huge number of supermassive black hole binaries at nanohertz frequencies? So this is a kind of cute derivation, which gives you a huge number of supermassive black hole binaries. It's not meant to be exact. It's just supposed to motivate the fact that, you know, we're not crazy for looking for the gravitational wave background signal. So because my eyesight is in this intermediate phase of being good and not good at the same time, I'm going to take off my glasses when I'm writing. And if you have a question, then I'm going to put them back on again. And so please, if you have a question, like feel free to really try to get my attention. Or say like, Chiara Mingarelli, over here, all right? The Italians know how to say it right. If you're American, you can say Chiara. Just don't say Chiara, okay? All right, got it. So here we go with this order of magnitude estimate. So what we're gonna do is that we're gonna show that there is some number of sources and some frequency bin. And this is the number of sources here, number of sources, and then this is your frequency bin, which is 1 over your observing time. And our entertaining photographer is back, I think. There she is, wonderful. Okay, and so this is then equal to dn by df, and so I can write that this delta n is equal to dn by df delta f. And we can do one of our favorite things, which I'm sure you guys have done tons of times this week, and that's multiply by 1. So I'm going to write that this is dn by dt times dt by df delta f. This is to the -1. And this is f dot, right? Your gravitational wave frequency derivative. Okay, so where do I go from here? The blackboards at Yale are even stiffer, so this is nothing to me. Okay, so the next thing that we do is that we plug in the value for f dot, and we leave out all of the prefactors, any kind of factor of pi or 196 over 32 or whatever. We're going to let this frequency, of course, be the gravitational wave frequency, just to be clear. And we know that f dot GW is proportional to the chirp mass to the 5/3 times the gravitational wave frequency to the 11/3. Yeah.
Why is the TTDF to the -1? Don't we need the DT split as well?
Oh yeah, sorry. I think I wrote it as df by dt, but to the -1 in my notes. They should definitely cancel out. Thanks, Emiko. Someone's had enough coffee and it's not me. Okay, very good. So now I can write delta n is proportional to this chirp mass to the -5/3, the frequency to the -11/3, and delta f times some dn by dt. This is a merger rate, right? So what is dn by dt? How can we how can we figure out what the merger rate is for supermassive black hole binaries in a really easy way? There's no points for being fancy here. How do we do this in a really dumb way? How many galaxies are there in the universe? Okay, 10 to the 11. Okay. So dn by dt, we're going to say there's some number of galaxies in the universe. And how many mergers does each galaxy have? It's 1 or 10, right? So, and we're talking about major mergers because this is for a stochastic background. So these are massive galaxy mergers. So do massive galaxies merge on average 1 time or 10 times in their lives? Yes, okay, good. Right, so times the number of mergers that they have, very good. And then divided by some dt. What's dt? What's the age of the universe? What's the age of the universe? Hubble time, right, over h naught. So, very good. I see that you guys are all doing very well. So this gives you 10 to the 11 galaxies times about 1 merger per galaxy divided by 10 to the 10 years. And that gives you something like 10 mergers per year, more or less. Okay, we're going to switch to the middle board now. Okay, so we have dn by dt is about 10 mergers per year. If you don't, it's a poor woman's calculation. If you don't want to do anything too fancy, at least it gives you a number. So that means that we can write down this delta n as some, right? We wrote it up here. This is the number of supermassive black hole binaries that we're going to have as a function of mass of your binary, gravitational wave frequency, size of your frequency bins, and merger rate. Okay, so what I'm going to do now is do something that astronomers taught me how to do, and that's to write down this kind of scaling relation where I plug in fiducial numbers, and then out in the front pops the number that works for specific values that you can then scale up or down. So I'll save the big reveal for the number for the end, but this goes like big reveal surprise number, right? So let's say chirp mass for 10 to the 9 solar mass binaries to the minus 5/3, and then frequency. Ooh, I have a hiccup. And we'll just say at 10 to the minus 8 hertz, 10 nanohertz to the minus 11/3, and then this goes like frequency is 1 over your observing time. So this is observing time to the minus 1. And let's just say that we have 10 years of observations in your pulsar timing array. And we estimated that our dn by dt is something like 10 mergers a year. Okay, so if you put all these numbers in, you get something that's like around 10 to the 12 binaries, which is, admittedly insane because there's 10 to the 11 galaxies in the universe, right? The point is that the number is big, right? We do expect there to be a stochastic background at these nanohertz frequencies that are measurable with frequency bins of the order of 10 years. You can play with these numbers back and forth. You can make better estimates. There's a lot of things that you can do better, but in terms of an order of magnitude calculation, it helps you to understand the fact that there should be many, many, many supermassive black hole binaries if you believe that they come from galaxy mergers. Okay, so how do we find these merging supermassive black hole binaries and the stochastic background that they create? So the Hellings and Downs curve is the effective waveform, right, for the stochastic background. It was the thing that we had to see in order to believe that there was a gravitational wave background. And the Hellings and Downs curve is a purely geometric argument. So I'm going to start by setting up the geometry of our coordinate system. Okay, so we have a pulsar on the z-axis. And I said Z, I'm Canadian, just in case you guys were wondering about my name and accent. Okay, so I have one pulsar here on the z-axis. We'll call this pulsar A. My pulsars look like little candies. And then we have our second pulsar here. So that's A. And then the second pulsar, it's here, pulsar B. At some distance, LB. This one's at some distance, LA. They're separated by some angle zeta. And here we have our phi angle projected down. And then along this line here, can you guys see, is this dash too finely dashed? Yes, too finely dashed? Okay, so I can. Let's use orange. Orange seems to be effective here. Is this better? Okay, so here omega hat is the direction of gravitational wave propagation. That's this one. And it has principal components M and N. So let's see, I'm going to move omega hat to here. This guy is omega hat. This guy is M hat. This guy is N hat. And M hat cross N hat is omega hat. Okay, so what else do I need to tell you? Oh, this angle here is theta. And I think that now we have enough to start writing down our coordinate system for the Hellings and Downs curve. Okay, good. So in this coordinate system that I just defined here, someone have a question? Yeah, omega is going away from us. So omega hat is the direction of gravitation. Wait, it's the direction of gravitational wave propagation. Did I put that the wrong way? And minus omega hat is the direction to the source. Yeah. The way that I did it, yeah. So this is the direction to the, it's the direction of gravitational wave propagation. I'm not going to start making changes. Yeah, omega hat is the direction of gravitational wave propagation. Okay, so now we can write down our coordinate system specifically in full and glorious detail in terms of actual angles that we've defined here. So M hat is sine phi minus cos phi 0. N hat is cos theta, cos phi, cos theta, sine phi, minus sine theta. Omega hat is sine theta, cos phi, sine theta, sine phi, cos theta. The directions to the pulsars are going to be PA and PB, where A is the direction to pulsar A and PB is the direction to pulsar B. So pulsar A is aligned with the z-axis and is pointing straight up. And this is going to make our life really easy because it makes this coordinate 0, 0, 1. And pulsar B is at some angle away, sine zeta, 0, and cos zeta. At some point, my zetas might turn into x's. And if you're Greek, I'm really sorry. But sometimes it just, I want to make loops and I can't stop. Okay, so this is our coordinate system. And I'm going to leave this up here, hopefully in the light. There we go. So the PTA response, yeah, I'm not going to use that right now. Well, yeah, okay. So a pulsar timing array's response to gravitational waves is given by the following. You have your Hij Tx is equal to some E plus, which is your polarization tensor, Ij, omega hat, H plus, and then your signal at some time t and minus omega hat dot x. And then you have your cross polarization with similar arguments. H cross t minus omega hat dot x. And the polarization tensors, this Pol N is polarization, is a short form for polarization, are defined as E plus Ij, and it's related to M and N, right? These principal components. So this is Mi Mj minus the dot product of Ni and J, and cross, I might just put it here. Well, these are both functions of omega hat. Just pretend I didn't forget it. K, and then Ij is equal to Mi. Here you have the cross terms, N hat J plus N hat I M J. Okay, so if we now consider a gravitational wave that's propagating through the galaxy, it's going to perturb this Earth pulsar baseline, right? We're going to see a change in the proper distance between the Earth and the pulsar. Before I keep going, can you guys read this? Is it big enough? It's legible. I pressed hard enough. Okay, very good. And so the difference in strain between the Earth and the pulsar as this gravitational wave is propagating through the galaxy is a delta Hij. And that's just equal to the perturbation at the Earth minus the perturbation at the pulsar. P time at the pulsar and omega hat. Okay. So this here is the time at the Earth. Time at Earth. And this is your time at the pulsar. Pulsar. Very good. So each perturbation introduces a fractional frequency shift in the pulsars across the array. And we can write that down as the following. We have Z of t and omega hat is this fractional frequency difference. So we're going to use nu for the frequency, nu of t minus nu naught, which is the rest frequency. And this is equal to 1/2 pi pj over 1 plus omega hat dot p hat delta Hij of t and omega hat. Okay, so here, this is for each pulsar. So I could put a little subscript A for here, or a little subscript B for here, but then that makes a lot of subscripts. And then you'll go back later and be like, what was A and what was B? So I'm not going to put them in here, but this is for a specific pulsar. This is the fractional frequency shift induced by a gravitational wave coming from direction omega hat, and then projecting its signal onto one pulsar. Okay, and then again, this delta Hij is this difference between the time at the Earth and the time at the pulsar, and it depends intrinsically on where your pulsar is on the sky with regards to omega hat, or the gravitational wave. You can also see that explicitly in this expression here. Okay, so if you have a signal, like a stochastic background that's coming from all directions, what do you do to this fractional frequency shift? Oh, it's time for my glasses. What happens? If I want to say that this is coming from all directions on the sky, what do I do? Someone's trying to take a picture? Close. I'll give you average. We integrate over the whole sky. Marginalize. Okay, great. Very good. So we take it, and now we just have a time dependence because we want to integrate this over d omega hat because it's a background. And this is really the trick that we do throughout everything in PTAs when we're trying to derive these angular response functions, is that we do it for one gravitational wave, and then we integrate it over the whole sky to understand what the response is to a gravitational wave background. So if you know how it works for one pulsar, you take that answer, you integrate it over the two sphere, and you're done. So here you have z of t and omega hat. You integrate out omega hat, and then you get your answer. And the residual, which I talked about in my last lecture, does anyone remember what residuals are? People who are working in finance or planning to go to finance, you do not know the answer. It's a different kind of residual. No? No hedge fund people? Okay. The residuals are the expected minus the actual arrival times. Do you remember I showed you that long data stream that was like multicolored with the different observing frequencies and all of the dots were really close to zero? Those were residuals. So these residuals are what happen when you integrate over your observing time in dt prime. I'm just using a dummy prime index here. When you integrate these redshifts. Okay, so we're getting close. So we now want to know what the strain is for a stochastic background. And we integrated this response over the whole sky. And so now what we have to do is to calculate the sum from n plane waves that are coming from different directions omega hat. So now we want to work on the Hij term. Now we know how the pulsars respond. Now let's see what's happening with our source of gravitational waves. So this Hij total as a function t and x is just the sum of all of the incoming plane waves from n equals 1 to n of Hij and t minus omega hat n dot x. Okay, so these residuals are the actual measurements that we make at the telescopes, right? So you saw them in my previous lecture. They kind of look like DNA if you squint at them. But this is, I go to a telescope, I point my telescope at a specific part on the sky where the pulsar is. I then time this pulsar for 30 minutes, and I get a time of arrival. And I take the expected time of arrival from that pulsar, and I subtract it from the actual time of arrival from that pulsar, and it gives me the residual. So now you can see really clearly how the residuals contain the signature of the gravitational wave background, and really of any gravitational wave. The way that we're constructing this is for a background, but you could also construct this for an incoming plane wave. You just don't integrate over the sky. Okay? All right, I'm going to see if at least 20% of you are nodding. No? Yes? All right, I'll take 10%. I'm not too proud. Okay, good. Now let's tie this all together. So we have our Hij of t and x. And now what we're going to do is try to do the cross correlation of the residual. So I'm setting up a plane wave expansion for this metric perturbation that's produced by a stochastic background. So what I'm going to do is try to write this in a way that makes sense, I'm going to leave space for additional terms. Okay, so I have my incoming plane wave, and I'm integrating it over the whole sky, which is why I have this d omega hat over s squared, right? This is the sine theta, d theta, d phi. This is you integrating over the sky. So here you're integrating theta from 0 to pi, and you're integrating phi from 0 to 2 pi, just to be super clear. I'm not withholding any details from you guys. Then you have your HA. Remember, these are a function of your polarizations. And now we're looking at a Fourier transform. So we're in F e to the 2 pi I. This is going to get small. T minus omega hat dot x. Oh dear. Okay. I'm just going to rewrite this, because this is where I get the pulsar terms, right? And we both really want to talk about the pulsar terms. Okay, so let me just try to rewrite this as a sum over the polarizations A. So these A's are the plus and cross polarizations. And we're integrating from minus infinity to plus infinity in df. We're integrating over the whole sky. So that's in d omega hat. And now we have our Fourier amplitudes, these HAs of f and omega hat. That's right. E to the 2 pi I f t minus omega hat dot x. And now we have the extra space I needed. And then the polarization tensor, oh, excuse me, at the end here. Okay, so I want you to remember that A is just a short form for plus and cross. And for those of you who are interested in extensions of general relativity and are thinking about other things like breathing modes, right? That's where you would enter your breathing mode into this kind of equation, right? When you're summing over the polarizations, this is where you would add your extension to general relativity. So for breathing modes, they don't exist on their own. You need plus and cross in breathing mode. But here is exactly where you would add that to your equation if you wanted to think about additional polarizations for gravitational waves. Okay. So let's look at these Fourier amplitudes. So here, I think I already told you that, yeah, omega hat is the direction of gravitational wave propagation. These are your gravitational wave polarization tensors. There's two independent polarizations, plus and cross. And so let's look at the statistics of these HAs. So the expectation value for HA of F and omega hat and HA prime of some F prime omega hat prime star is equal to delta squared of omega hat prime, delta A prime, delta F minus F prime, H of F, and P of omega hat. Okay, so now we're going to go back over here. And I'll tell you what all of those things are and why we care about them. Okay, so this delta squared omega hat prime is just delta cos theta minus cos theta prime and phi minus phi prime in our original coordinates that we're using. That's the covariant delta function on the two sphere. covariant delta function on the two-sphere. So this means that radiation that comes from different directions are independent. So we're already implicitly assuming that the background is isotropic. Okay, then what we do is that we factorize the power spectrum into these two components, this h of f and p of omega hat. So h of f tells us what the spectral content of the radiation is, and this is what tomorrow's lecture is all about. So we factorized some sort of power distribution to be an h of f and a p of omega hat. So this is where the characteristic strain comes in, and that's tomorrow's lecture. And this is where you can get really fancy with how your radiation is coming in on the sky. So if you assume that the background is isotropic, or statistically isotropic, then you can just ignore this term here because your angular power distribution is going to be some monopole or some y00. But if you believe that there's some sort of anisotropy in the background, and because we believe it to be astrophysical, it makes sense that there are some sources that are more nearby than other sources. These can induce anisotropy, or there can be hotspots on the sky. This is where you would put in your expansion, for example, in spherical harmonics, and then decompose the power of the gravitational wave background on, for example, a basis of spherical harmonics. You can also do this in a pixel basis. In fact, Neil and Ricker van Hasteren were the first ones to do that back in 2014. There's lots of different bases that you can use. Spherical harmonics are normally the easiest for everyone to understand. So that's where this enters the equation. Okay, but for here, because I'm just doing this from ground zero, I'm going to assume that this is 1. If in your heart you really want to think about spherical harmonics, you can assume it's 1 over root 4 pi. But we're basically just going to ignore this term for now. Okay, so now let's try to get even more concrete with our expressions. We've kind of gone on this journey where I set up this coordinate system for you. I'm telling you where the pulsars are. I tell you where the gravitational waves are. I tell you about the principal components of the gravitational waves, how your pulsars respond to gravitational waves, and then how your measurements at your telescopes encode that response to the gravitational waves. And so now what we need to do is to actually write out something concrete that tells us how these antenna beam patterns, which I define as those F pluses and F crosses, can in turn be written as a function of our geometry and then integrated to give you the Hellings and Downs curve. Okay, so in order to do this, I need to be more concrete with my choice of time variables over here. Here I did everything in terms of some t and some x, and you can do it however you want, but let's put ourselves in a very specific part of the parameter space. So I'll define the center of this coordinate system to be the origin here at the Earth. So to do that, I define the time at the pulsar to be the time at the Earth minus the distance to the pulsar. And the time at the Earth I'll just call t, and I'm going to drop the subscript. So this is t minus L. I'll just be very careful and write that down here. TE is just t. Then for my x vector, the position or the distance to the pulsar is L times p hat. And the Earth is at the center of our coordinate system. Okay, wonderful. So now we can actually start to make some real progress in terms of writing down something concrete. And I haven't even invoked a Hilbert space yet. No? Okay. All right. So I'm going to go back to my expression in this reference frame that I created that I call the computational frame. And you'll see why I call it the computational frame soon. I go back to my Hij T of omega hat. And now I can do some real work. So now I'm summing over the two polarizations and I'm still integrating in frequency, df, and I have my polarization tensors, Ea, Ij, which are a function of omega hat. And I have my Fourier amplitudes here, and then I have my e to the 2 pi I ft times 1 minus e to minus 2 pi I fl 1 plus omega hat dot p hat. Okay, so now we remember that if we want to figure out what this fractional frequency shift is for a background, we integrate z over d omega hat. And we put it back into this equation above. So now we have integral in frequency. And I'm introducing a new notation here, which are the antenna response functions, your f pluses and f crosses. This is pretty standard, so I wouldn't be surprised if you've seen this before. But if you've seen this before, you're probably relieved that it's something that you've seen before. And you feel really smart because you know what it is, which is wonderful. Okay, so HA e to the 2 pi I f t, and then I again have the same bracket down here, which is 1 minus e to the 2 pi I f L 1 plus omega hat dot p hat. So just to remind you, the reason that I have a 1 here is because the Earth is at the center of our coordinate system. So e to the power of 0 is 1, right? This is the Earth term, and this is the pulsar term, right? So the pulsar term depends intrinsically on the distance to the pulsar, the frequency that you're considering, and the angle that the pulsar makes with the Earth gravitational wave source pulsar baseline. And you're probably thinking, well, wait, for a stochastic background, it shouldn't matter. This is what you have before you integrate your whole function over the sky. So it intrinsically includes those factors, but you're right that you then integrate over them. Okay. Now, this is 12. Wait, do I only have 5 minutes left? No. How much time do I have left? Oh my God. I was like, I was really into it, guys. I got carried away. Okay, good. We'll totally make it. Okay, so these FAs are really important. So these are called the antenna beam patterns. They're sometimes called detector response functions. It's the same thing. You just kind of call them different things. So pulsar timing came from the radio astronomy community. And so they think of them as detector response functions. And sometimes physicists like to think about them as antenna beam patterns, but it's the same thing. So the way that you define these, you can probably figure it out on your own because it's just a relabeling of terms that are already in the equation, but I'll save you a little bit of time. So it's 1/2 pi pj over 1 plus omega hat dot p hat with your polarization tensor Eij omega hat. Okay. We can also then write these as dot products of your m's and n's. So we can write the plus pattern explicitly. We don't have to, but it's nice to see it as 1/2 m dot p squared minus n hat dot p hat squared over 1 plus omega hat dot p hat. And your cross polarization is m hat dot p hat and then n hat dot p hat over 1 plus omega hat dot p hat. Okay. And so again, if you're doing an extension to general relativity, you're going to have a new expression for your antenna beam patterns, right? Because it depends on your polarization tensors. And those come into play here. So just if anyone is curious about that, that's how you would do it. Okay, now we're at the beefy part of the calculation where we actually cross-correlate the residuals. So we've spent a lot of time building up how the gravitational waves interact with your pulsars, how we are projecting the gravitational wave onto the pulsars and using the pulsars as gravitational wave antennas. And now what we're trying to understand is how can I write down the residuals from the pulsars as a function of these antenna beam patterns for a gravitational wave background. So the last step is to take all of these residuals here and to cross-correlate them so that I theoretically understand how the gravitational wave background is manifesting in these pulsar residuals. All right, I'm going to look for a 10% nodding heads before I move on. Whoa, I think I got 12% that time. That's amazing. Okay, good. So I'll write down the first expression here, and then I'll continue it over there. So what we're looking for are these cross-correlated timing residuals. Now we're going to do a residual from pulsar A at some time, Tj, times the residual from pulsar B at some time, Tk. And that's equal to some dt prime, just again, the primes are just dummy indices, some dk, this is j, this is j, this is k, this is k. Good. That's my own error correcting code. dt prime prime, and then we have the two redshifts, right? Because we know that the residuals are related to the integrated redshift on the sky. So this is z star a t prime and zb t double prime. And we're averaging this. Okay. Now, I don't know. Can you guys see if I write on this last line? Okay, I saw one enthusiastic head nod. That was very blurry, and that's good enough for me. Okay. So what this gives you then is your integral Tj in dt prime, your integral in Tk, dt double prime. And now you have your Fourier transforms. So you have your minus infinity to plus infinity in df prime, and then df prime prime, because we're a sucker for punishment in this field. And then you have z star a f prime zb f double prime and e to the minus I2 pi. And then the difference between your ft terms. So this is f prime t prime minus f prime prime t prime prime. You can ask me again what that is later if this isn't super clear for you. Okay. Okay. So now we get to the good part, which is that this is equal to your Tj integration, dt prime, tk, dt double prime, your integral in df And I have e to the minus 2 pi. I think I put I in front first. F t minus t prime prime, h of f times gamma AB of f. Okay. So I know that the f's have to be the same. F prime is equal to f prime prime, which is equal to f. I put that in here. My integral is in df. I now have two parts of my residuals that pop out. One is h of f, which is the spectral content of the gravitational wave background. And again, that's the thing that has the characteristic strain in it. And then the second part is gamma. Gamma is our overlap reduction function. So gamma AB, I define, which is actually a function of frequency, as the integral in d omega hat of something that I call kappa AB f of omega hat times the sum over your polarizations of your antenna beam patterns for each pulsar. So here I label pulsar A as little a, and then pulsar B's antenna response function. And here, this kappa term, I think it was the only good symbol that was left when I wrote it down back in 2013, is the difference between the Earth and the pulsar. So this is the Earth term minus the pulsar term for both pulsars. 1 minus e to the I 2 pi FLA, where LA is the distance to pulsar A, 1 plus omega hat dot p hat A, and then similarly for pulsar B, e to the minus 2 pi FLB, 1 plus omega hat dot p hat B. Okay. So this is the overlap reduction function, which eventually gives you the Hellings and Downs curve. But you see how it comes out from cross-correlating the residuals, right, which you get from integrating your fractional frequency shifts over the sky. And when you do that, you have two parts. You have these antenna beam patterns, and to get this omega hat term, we integrate them over the whole sky. So again, here, because I'm integrating in d omega hat and I don't have some p of omega hat, I'm implicitly assuming that the background is isotropic, right? That there's no angular dependence here. If the background is anisotropic and you want to rederive these functions, then what you do is that you can add your YLMs, for example, here, a series of YLMs, and you can go up to whatever point you want and rederive this correlation function for anisotropic backgrounds. So there's a few comments, I think, that we want to make about this kappa term, because this is the only point where you get the pulsar distances that come into your gravitational wave background measurement. Okay, so one thing that you can understand, I think, quite clearly here, if you have the frequency times the distance to the pulsar that's much greater than 1, this term rapidly goes to 0, right? You have some e to the minus big thing, that's going to give you 0. Yeah, y'all agree? Very good. What about this guy? That's e to the something positive, right? So it's not so obvious, I think, when you look at this at first, that this thing just doesn't blow up completely. And that's where you're saved by the Riemann-Lebesgue lemma, which tells you that these terms here are all rapidly oscillatory. And so this thing also eventually goes to 0. If you remember, I told you during my previous lecture that there was a disagreement over a bottle of wine with Mingarelli number 2, who's a mathematician. It was about this. I was integrating this function here, and I was like, well, if I take FL equals to 10, Everything seems to work out fine. I, don't have to take into account these terms. I showed numerically everything was fine. And he was like, but what if FL is equal to 10,001? Like you have to do this for all cases. You can't just do for a few cases. And he's like, don't worry, it's a straightforward application of the Riemann-Lebesgue lemma that I taught you in your first year calculus class. And I was like, I have no memory of my first year calculus class, nor the Riemann-Lebesgue lemma. But it did save us. So the only time that you see here that the pulsar terms become important, and again, I'll remind you, you have the 1 because you're choosing the center of your coordinate system to be at an L0 to be the Earth. So this is an e to the 0 term, which is why it's 1. And then you're subtracting your pulsar term, which is some distance away from the Earth, LA, and the term is modulated by the angle that your incoming gravitational wave makes with your pulsar. And it's true for pulsar A, and it's true for pulsar B. And again, you have these two pulsars because you're cross-correlating the pulsar residuals here. You're looking for whatever's common in these two residuals. So the only time that this pulsar term becomes important is for the autocorrelation, right? And you can prove this to yourself numerically, but I'll show you a kind of straightforward way of understanding it analytically, because that's my favorite. It's here. So if you have the autocorrelation, it means that you're correlating the pulsar with itself. And that means that pulsar A is equal to pulsar B, and LA is equal to LB. Okay. So what are some of the consequences? What happens to this kappa term if I look at the autocorrelation? Anyone has thought about pulsar distances before, maybe you already know the answer. So what happens for kappa AA or kappa AB? Well, I get 1, and then I have another term that gives me another factor of 1, so that's 2, and then I have a cross term that sort of looks like a cosine, right? If you guys remember your basic geometric arguments. So this actually gives you 2 minus 2 cos 2 pi FL, yeah, that's right. 1 plus cos theta, which is just 1 plus omega hat dot p hat in this particular coordinate system. That's one bracket closed, that's another bracket closed. Okay, good. But again, here, this term is going to be, this FL is very large. This term is rapidly oscillating, and it's bounded by this factor of 2. So this is about a factor of 2 here. So we say that this is approximately 2 for the autocorrelation. And so instead of writing this kappa hat everywhere with all of your pulsar terms, you recognize that the pulsar terms and distances to pulsars in the context of the gravitational wave background are only important for the autocorrelation. And so we write this as 1 plus delta AB. And so when pulsar A equals pulsar B, you have twice your overlap reduction function, or twice gamma. And when it's not, you don't worry about it. If you want to be fancy, you can put this term in, which is fine, but it really rapidly goes to 0. In fact, it gives you a nice kind of spherical Bessel function, and it looks cool, but it really doesn't matter. Okay, so we can now rewrite this overlap reduction function as 1 plus delta AB for the pulsar terms times this integral in d omega hat of f plus and f cross. So we'll have FA A and FAB. And I'm not writing the omega hat dependencies anymore. I think it's clear. Okay, so what are one of the fun things that you might have noticed if some of you have been maybe trying to compute these in your heads and notice that they're kind of close to each other, right, on the board? what do I get for m hat dot p hat? It's not a trick. Yes, good. Very good. That's why I chose that particular coordinate system called the computational frame, because it nullifies the cross response function. It's 0, which is wonderful because it's one less thing for you to compute. So now, in fact, you only have to compute and integrate the plus response because the cross one is 0. It's not black magic, it's just math. Okay, so let's go back over here. And I have 5 minutes left? Yes. We're gonna finish on time, guys, and then you're gonna go have some food and be so happy that you saw the Hellings and Downs curve. Oh, wait, what?
You have 15.
15? Wait. Okay, 15, great. Then I can tell you more stories as we go. Okay, so by construction, the cross response is 0. And when I do all of these dot products, which I'm sure by now everyone knows how to do, I'll just give you what the answers are. F plus A is equal to minus 1/2, 1 minus cos theta. And then F cross B is awful. And I don't think I need it, so I'm not going to write it down. And then let's just do F plus B. F plus B is the tough one. That's 1/2 sine phi sine zeta minus sine zeta. Oh, it was almost an XC. Sine zeta cos theta cos phi minus sine theta cos zeta squared. Oh. This is F plus B because the crosses we don't care about. Yeah. And I divide this by 1 plus cos theta cos zeta plus sine theta sine zeta cos phi. And now I have something really concrete that I can integrate, right? Because to get the overlap reduction function, or gamma, I multiply these two things together and I integrate them over omega hat. So I have these two factors of 1/2 and a factor of -1. So I get an overall factor of -1/4. And I have my pulsar term contributions that are as 1 plus delta AB. D omega hat is sine theta, d theta, d phi. So when I now integrate it, I integrate from 0 to pi and d theta sine theta. And I now integrate from 0 to 2 pi in d phi of the rest of this nasty function that you guys can plug in. Ugh. And when you integrate it, your overlap reduction function becomes root pi over 2, 1 plus the cosine of zeta over 3 zeta plus 4 times 1 minus cos zeta log of sine. My zetas have become xc's as promised over 2. And then I have my pulsar terms at the end, 1 plus delta AB. Okay, so this is the Hellings and Downs curve. This is the mathematical expression for the Hellings and Downs curve. And now you know exactly where it comes from. So you can already see by eye that this isn't going to give you 1 for the autocorrelation. You have to normalize it by a factor of 4 root pi over 3 for it to give you 1. And that's just a normalization factor that we throw in so that it looks nice. When you draw it, this is pi over 2, this is pi, this is a half, this is 1. You have this kind of discontinuity that's not really a discontinuity because you have the cosine term that makes things continuous, but for all intents and purposes, it looks kind of like this, where we know that the minimum is shifted a little bit and that the second point where it comes up is 0.25. Why is it 0.25? It's actually half of what you get for epsilon away from the autocorrelation. And now I can show you why, because I have a little bit of time. Okay. So for F plus A, F plus B, this gives you a factor of 1/2, 1 minus cos theta, 1/2, 1 minus cos theta, this is a quarter, 1 minus cosine squared theta. So 1 minus cos theta squared. Very good. Okay, so when you integrate this over the sky, you get your 1/4 that comes out. And you're integrating this in d theta, sine theta, 1 minus cos theta squared. The response is 2/3. Now, when zeta is equal to pi, the antenna beam pattern, sorry, this is for 0, well, ish. Then your antenna response functions are FA, FB, and then you have 1/2, 1 minus cos theta, and then 1/2, 1 minus cos of theta minus pi, or pi minus theta. And this is 1/4 sine squared theta. And when you integrate this over theta, you get 1/4 pi d theta sine theta, and then your sine squared theta term. And this is equal to 1/3. So you can see that regardless of whatever your choice of normalization is, you're always going to have your endpoint, a pi, be 1/2 of your beginning point at 0. Maybe this has been burning in your imaginations for many years. Maybe it hasn't, but now you'll know. Okay. The other thing that I want to point out very quickly are potential pathologies when you're integrating the overlap reduction functions. So you have this 1/1 plus omega hat dot p hat term that's all over the place, but now it's gone. Do I have any of them left? I do not. That's okay. You might be wondering about what happens when there are singularities in your antenna beam patterns. Or maybe you thought about this when I was writing them down, right? You have all of these terms that look like 1 plus omega hat dot p hat. Well, let's think about some weird things that can happen here, right? When is this function maximal? I thought someone put their hand up. When does it blow up? When omega hat dot p hat's -1, right? I don't ask you guys trick questions, don't worry. Okay, so this blows up when omega hat dot p hat is equal to -1. And that means that your pulsar is aligned with the direction to your gravitational wave source, because the direction of gravitational wave propagation is omega hat, which means the direction to your gravitational wave source is minus omega hat. So when this is equal to -1, it's because omega hat dot p hat are aligned. And so this gives you the maximum response that your function can have. When you take into account the pulsar terms, you see that the divergences go away, and you get on average something like a factor of 4-ish additional response. The other thing that you might be worried about is when it's equal to 1, it's quite minimal. When it's equal to 0, again, nobody cares. Okay. All right, I think I'll stop here and I'll just summarize by saying that in today's lecture, you learned how your pulsars respond to an incoming gravitational wave source in this geometry. We then took that response from your incoming gravitational wave source and integrated it over the whole sky to give you the response to an isotropic and Einsteinian gravitational wave background. But all those assumptions can be relaxed. If your research is going in those directions, I gave you jumping off points for you to take your work in those different directions using pulsar timing arrays. I showed you how you can compute these antenna response functions in a particular reference frame that's ideally suited for computing your antenna beam patterns because you get nice zero cancellations. And I derived the Hellings and Downs curve for you and showed you why. It starts at 1/2 instead of 1, because we know that you only have pulsar distances that are important for the autocorrelation and for the pulsar term here. And I showed you how you get half of your initial response function at pi versus 0. So if you have any other questions about the Hellings and Downs curve or the more general anisotropic overlap reduction functions, I'm very, very happy to talk to you about it. So thank you all for your attention.